So today I want to finish the analysis of the dual fitting analysis of the greedy algorithm for set cover or weighted set cover. And I'll do one other very simple example for dual fitting, namely unweighted vertex cover. And so the next homework is going to be out tonight, and you'll see a problem related to that, to vertex cover. Then I want to talk a little bit about a limitation of this whole LP framework for approximation algorithms. Okay, so I'm going to introduce something called the integrality gap of an LP relaxation. And then I'm going to talk about more approximation algorithms, namely polynomial time approximation schemes. And that's where we don't just want, say, a 2 or log n approximation, but we want a 1 plus epsilon approximation where epsilon is given in the beginning. Okay, so how do we get, for any fixed epsilon, a polynomial time approximation? Sometimes that's not possible, but we'll see an example where that is possible. Okay, so last time I defined the set cover problem, or the weighted set cover problem. There are m sets. Each one is a subset of the universe. The universe for us is 1 up to n. And a set S has a cost CS. And the goal, given an input, the goal is to find a subcollection of the input sets which covers the entire universe. Okay, you must cover the universe, and you want to do it as cheaply as possible, minimize the sum of costs. Okay, the sum of costs of sets you take. So the greedy algorithm, well, in the unweighted case, I think people have seen, if you've taken CS124, you've seen the greedy algorithm. For the unweighted case is you just keep taking the set that covers the most new elements. Okay, but when you have costs on the sets, then you just slightly alter that. You pick the set, as long as there's an uncovered element, you pick the set which minimizes the ratio between its cost and the number of new elements you get to cover by picking it. Okay, and theorem greedy is a log n approximation. We'll even see it get something slightly better. Just some history, I guess. In the unweighted case, when all the costs are 1, that's what I mean by unweighted. This greedy algorithm is due to Johnson back in '74, I think. Who's scribing today? Okay, great. And also, I believe independently, at least they didn't cite each other, in discrete math, 75. And in the weighted case, I don't know how to pronounce this name. And that was in '79. Okay, so we're going to take a primal dual look at this, at analyzing this algorithm. Okay, so if you took CS124, we did analyze it there. We didn't talk about primal dual, but you can take a primal dual look. And for one of the homework problems that I'm going to release soon for vertex cover, it's going to be for weighted vertex cover. Even it's not just an issue of the analysis. Even to come up with the algorithm, I think it helps you to have a primal dual look at the problem. Okay. Okay, so the LP relaxation for set cover, I said last time, in the primal, we want to minimize the sum over S of CS times XS, where XS is 1 if you take the set 0 otherwise, subject to, for all I from 1 to n, you need that the sum over sets containing I of XS is at least 1, and that for all S, XS is at least 0. Yeah?
So when you say the LP relaxation, does that mean there's a unique?
No, so that's a very good point. Yeah, I shouldn't have said the LP relaxation. So an LP relaxation. Okay, so so the set cover problem is actually this problem, but where you have the constraint that XS is either 0 or 1, and we relax that to just put a linear inequality. But you could imagine formulating it another way and getting another LP relaxation of another formulation of the same problem, and maybe using that LP relaxation would give you better results. So there's actually, I'm not going to get into it in this class, but there's actually a formal way of doing this. So given some integer programming optimization problem where you have integer constraints, there's a systematic way of converting the LP of getting more and more refined LP relaxations, which become better and better approximations to the integer constraints. So if you want to read more about this, you Google for the Shirali-Adams hierarchy. Okay, so I'm not going to talk about that in class, but and you can show that eventually this thing becomes the integer program after, but then by that time you've blown up the LP to exponential size. So, okay. So that's the primal. And the dual is we want to maximize the sum of e going from 1 to n of y sub e, subject to the constraint that for all sets S, the sum of elements in that set of ye is at most cs, and also y is a non-negative vector. Okay. So we'll do dual fitting. I think I mentioned this at the end of last time, but now I'm actually going to prove something. So dual fitting. We'll show how to maintain dual solution as we build a primal. Okay, so when we take a set S, okay, we're going to set x sub s to 1 in the primal, and 2 for each newly covered element E, we'll set y sub e to equal c sub s over the number of elements newly covered by S. Okay? So this is what we're going to do. Remember the usual thing. We know by weak duality that that any primal, if we have two feasible solutions, one for the primal, one for the dual, we know the primal cost is at least the dual cost, right? Where opt is sandwiched in between. But they have to be feasible. So as it turns out, this y might not be feasible, but we'll show that if you entry-wise just scale down by log n, it will become feasible. Okay, so let me write down some observations. First of all, the cost in the primal of x is the cost in the dual of y. Okay, we've rigged it that way. And we'll show that, in fact, we'll show y over the nth harmonic number is feasible for the dual. And that's going to imply law n approximation. And definitely, I should also say, I mean, I didn't say it. the primal will be feasible, right? The primal is feasible because we keep doing that while loop as long as there's a constraint that's violated. Okay, so now we just need to show this. So claim y over hk is feasible for the dual. So proof. So this constraint's never violated. The only trouble is this one. So we need to show that for all sets S, this summation is at most CS times log n. Need to show that for all S, the sum of E and S of YE is at most CS times log n, or actually times HN. What's K? There's no K here. Okay. So let's order the elements of S by when they're first covered. So E1, E2, EK, right? So let's say S has size K. Okay. So let's look at right before EI was covered. So what I want to say now, what I'm going to write after, when I finish the sentence, I want to basically say that, each one of these EIs at some point when it's first covered, it's going to get its Y sub E set, right? Now, EI might not get covered by S. It might get covered by someone else, okay? But I want to argue that when EI was covered, I want to argue that the price that we set to YE could not have been that high. I want an upper bound on that price. I'm calling my Y is for me the price vector. Okay. So what's some bound? Can anyone tell me a bound on the price of that we will assign to YE? So right before we covered EI, right? So EI is not covered, meaning we haven't chosen S yet, because S would have covered it. What would be the prices derived from choosing S at this point? CS over what?
The number of elements that would be covered at this point. So
And what's a lower bound on? Yeah, K minus I. K minus I plus 1, actually. Right? Right before EI was covered, we could have chosen S at price CS over K minus I plus 1. Okay? So we know that implies that the price of EI is at most CS over K minus I plus 1, right? That's what greedy does. It chooses the thing that gives us the lowest price. Whoops, I just lost one. So this implies that this summation right here, that star is at most C sub S times the sum I from 1 to K of 1 over I, which is exactly C sub S times HK. Okay? And K is the size of S. Remember, K here is the size of S, which is certainly at most n. In fact, we proved something stronger. We proved that if all the sets in your set system have size at most k, then actually greedy gives you a log k approximation. Okay, so that's it. I'll do just one more, an even shorter one. So one more. Vertex cover. So right, the input is an undirected graph G equals VE. Okay. I'll say this has size n, and that has size m. And the goal is to pick a subset of the vertices as small as possible, such that each edge in E is incident upon at least one vertex of S. Okay. So there's a greedy algorithm for this problem, which we said in 124, but I'll write it again. So greedy algorithm. And by the way, notice that vertex cover is actually a special case of set cover. Right? Do people agree with me? So someone tell me why. The edges are, so in set cover, there's a universe and there's a collection of sets. So what's the universe and what's the collection of sets? Right, yeah, so every vertex is a set, and every edge is an element of the universe. That's right, yeah, okay, good. So greedy, while there exists an uncovered edge, an edge E from U to V, add both U and V to E. And the claim is that greedy is a 2 approximation okay, and probably won't. I mean, we'll see one proof. There are many proofs. Well, we'll see a primal dual proof. But one proof is you can say, look, the set of vertices that I pick in this way form a match. Look at the edges that appear in this loop throughout every iteration. Okay, those edges form a matching. Okay, and therefore, the number of vertices we return in our set is twice the size of a particular matching. And then you can say any vertex cover size is lower bounded by the size of any matching. Okay, so, you look...
I am confused.
Yeah.
So, this algorithm up here,
Yeah.
for sets of size 2, it should give a free homotopy approximation?
Oh, yeah, okay, well, good. So the sets are the vertices. Right, so vertices can have high degree. Yeah, good. Yeah, I was also thinking that right when I wrote it, and then edges are contained in 2 sets, but But actually, that's a good point. So, for set cover, we said that if every set has size at most k, you get an HK approximation, like a long k approximation. But you could look at it the other way around too. You could say, well, what if every element is contained in at most k sets? So for that, you could get a k approximation. And how's that? Well, actually, it's going to be related to what I'm going to write now. So proof, if you really want to see one proof, we'll see another one. One proof, see the CS124 notes, or Google it or something. But I'll show you a different proof. Today we'll do primal dual. But other proof is primal dual. That's going to be helpful for something on the P set that will come out soon. So let me write the an LP relaxation, not the LP relaxation. So primal. The primal is minimize the sum I equals 1 to n, or the sum v goes from 1 to n of x sub v. So that's whether or not you take the vertex v into your vertex cover, subject to, for all edges E being uv in the set of edges, xu plus xv is at least 1, and x is at least 0, entry-wise. I mean, this should look familiar. It is the set cover LP, basically. Dual. We want to maximize the sum over edges of y sub e such that for all vertices v, the sum of an edges containing v of y sub e should be at most 1, and also y is entry-wise at least 0. Okay, so another way besides greedy, so the nice thing about the greedy algorithm is that it's pretty fast. You don't have to actually solve any linear programs. If you're willing to solve linear programs, which is slower, you could just solve this primal, right? And you could say, well, I'm going to get now some fractional solutions for the xu's, right? And then what I'll say is, look, for every one of these, now I need to get an integral solution. I need to choose which vertices to actually pick. For every one of these inequalities, either xu is at least a half or xv is at least a half. Okay, so I'll pick whichever one is at least a half. I'll put it into my set. Okay, and you've now at most doubled xv, so you've at most doubled the cost of the solution. So that's another 2 approximation for vertex cover, and that's also a k approximation for set cover if every set is contained in k elements, right? Because if every set is contained in k elements, remember these are the sets. You'll have a constraint here that involves k variables. Their sum is at least 1. One of them has to be at least 1 over k. So take the one which is at least 1 over k. And then now you'll get a k approximation. Okay, so that's it. So I want to show, though, a primal dual analysis of the combinatorial algorithm. We like combinatorial algorithms because they're faster than actually solving linear programs. So, so going back here, so now the proof using primal dual is again going to be dual fitting. When greedy takes some vertex v and capital V, set xv to 1, and also when greedy decides to cover an edge E, when greedy covers an edge E, which is uv in the edge set, set xu and xv both to 1. Actually, this isn't even going to be dual fitting. This is just pure primal dual because we're going to get feasibility automatically. Set y sub e to 1. Okay. So I think that's it. So both of these are feasible solutions. Okay. And whenever we increase the dual solution by 1, we increase the primal by at most 2. Possibly 1 if one of them was already taken. So it's a 2 approximation. Okay. So both feasible, but primal cost is at most twice dual cost, implies 2 approximation. So on the p-set, you'll see the case where the vertices are actually weighted. So you're trying to minimize xv times the cost of v. Then you need to think about what the greedy algorithm needs to change. You know, are you still going to take both? That's probably not a smart idea if one of them is way cheaper than the other one. But by reasoning about both the primal and the dual, you can get, you know, a decent algorithm. Okay, so that's all I want to say about approximation algorithms via dual fitting, or via primal dual. I want to move on to item 2, which is integrality gaps. Okay, so we could ask ourselves, you know, what is the limit of using some LP relaxation? Well, if you think about it, we always, so far, we achieve, in our proofs, we say we achieve cost at most some approximation factor alpha times the opt of the LP relaxation, right? And we can ask ourselves, well, can we improve alpha from log n to root log n or to a constant or something? But what if there is an inherent gap between the opt of the LP relaxation and the opt of the original integer program, right? So if there is some gap, so let's say we're looking at a minimization problem. If there is some gap that says opt of the LP is at most, you know, beta times opt beta times opt of the integer program for some particular instance, some particular input, you know, then such an argument, we can't hope to get better than a beta approximation. Then we cannot hope to achieve a ratio alpha which is strictly less than beta, right? So, I mean, I don't want to say that we can't hope to achieve it via any algorithm, but we can't achieve it via this particular LP relaxation, which goes back to your question, which is, you know, when you said, is the LP relaxation unique? You know, it's not. Sometimes if you're smarter and write down a better integer program to begin with, right, there might be many different ways to capture the problem as an integer program. If you write it in a smarter way and then do an LP relaxation of that, maybe a different LP relaxation could give a better approximation ratio. But this just gives you a limitation on using a particular LP relaxation. Okay, so for example, I mean, let me make this concrete example. Let me do them back in reverse order. First, I'll do vertex cover because it's simpler. Then I'll do set cover. So vertex cover. So where's the LP for vertex cover? It's right here. So what this constraint actually should have been is that, let me write it like this, for all u, xu is at least 0. What this constraint should have been is that xu is either 0 or 1, and we relaxed it to this, right? And I claim that actually once you do that relaxation, you already are losing a factor of 2. There are inputs where beta is 2, okay, or roughly 2, where opt for the fractional solution is only half the cost of opt for an integral solution. Okay. So what's an example? Take the complete graph on n vertices. I'm not good at drawing complete graphs. That was terrible. This doesn't even look right. OK. And I think I drew one twice. I drew two twice. Oh, right. I forgot it's a. Yeah, OK. That makes sense. OK. So opt of the fractional of the LP relaxation. Well, what can we do? We can put a half on every vertex, right? That will be a feasible solution. In fact, that is the optimal solution. That's n over 2, a half on each vertex. Whereas in the integer program, for the actual vertex cover problem, the best you can do is n minus 1. Okay, you take some vertex. You just take one vertex. Right. Take all vertices except 1. So n minus 1. Right. So if you take any solution with n over 2 or fewer vertices, that means there are at least 2 vertices left out, but then you're not covering the edge between them. Okay, so you need a cost at least n minus 1. So there's a gap of roughly 2. Okay, so if you're arguing using this LP relaxation, if you're somehow rounding solutions to that, then you're sort of out of luck.
So back on that first
Yeah.
section there, is it we can't hope to achieve alpha less than beta, or we can't hope to achieve the cost, like a different alpha? Is it the same alpha?
Yeah. So I'm saying if our way of coming up with this algorithm and analyzing it is to compare with the optimal solution of some LP relaxation, well, if the LP relaxation has a gap with the original integer program, and that gap is at least a factor of beta, then there's no way to achieve better than a beta approximation by this kind of comparison, right? Like if the way that we're analyzing our algorithm is to say, look, our algorithm never achieves cost more than alpha times opt of the linear program, well, you're not going to be able to achieve an alpha here that's better than beta, because the solution you're providing is an integral one, right? So in particular, the example which creates this gap, you're going to be off by at least beta, right? So that's what I mean. So yeah, the best beta you can achieve is usually called the integrality gap. It's like the max over all instances of the gap, and usually you parameterize instances by something like by the problem size. So like as a function of n, what's the worst gap that you could possibly have, or as a function of some other parameter of the problem. So we're going to see that, for example, for set cover, right? There we're going to parameterize by n, and we're going to say as a function of n, what's the worst gap that you can have. So we're going to give an example where you're off by a log n. Okay.
So in this case, the gap would be 2n minus 2 over n.
So yeah, here I'm really looking at the ratio. So yeah, it's as n gets big, the gap is approaching 2. Any other questions? Okay. Oops. Okay, so for another example, this one will be a little trickier. Set cover. I want to give a log n gap. Define n to be 2 to the q minus 1 for some integer q bigger than 0. Okay. And elements of the universe are in correspondence with elements of F2Q without 0. So what is this? These are vectors of length Q over F2, over 0, 1. So this is some vector space. Okay, so really I'm just saying, think of these as like bit strings of length Q, and adding them means bitwise XOR. And sets are also in correspondence with elements of F2Q, where the set corresponding to alpha, so let's say if alpha is in F2Q, so it's also some bit string of length Q, that implies that S sub alpha is the set of all E in the universe such that alpha dot E, this is the dot product, is equal to 1, mod 2. Okay? Are there questions about, feel free to, if I'm using some jargon that doesn't sound good to you, just ask me to clarify. Okay? Yeah.
Right, so I think that beta is 1 over alpha, right? Like, it's like the reciprocal.
Oh, is that right? So, oh yeah. I see what you mean. You can't hope to achieve alpha. Yeah, okay. Yeah, so opt of the IP.
So opt of IP is greater than equal to 1 over beta opt, or no?
Right. Yeah, okay. Yeah. So let me just think. So here, so if the LP is 1, the IP is 2. Oh, yeah, okay. So this beta is actually a half.
Yeah.
Yeah, okay. Yeah, good. So this 1 over beta is what I was calling the integrality gap. Okay. Very good. Yeah, thanks. All right, so here I have a vector of bits. Here I have a vector of bits. I'm taking their dot product. Okay, mod 2. Okay, good. So what am I going to try and claim? I want to claim that a fractional solution can actually cover all the elements with a cost of a constant. Okay. Whereas an integral solution has to have cost at least q. And q is about log n. So what's a fractional solution? What's a cheap fractional solution? Or let me ask first as a hint, for every element in the universe, how many sets contains it? How many sets contain it? Well, okay, so there are 2 to the q sets, and wait, how many contain it?
Oh, there are 2 to the q.
There are exactly 2 to the q sets. Half of them, right? Because in particular, I mean, one easy way to see that is if you pick alpha at random, then the probability that this dot product is 1 is a half, right? I mean, and that's because we removed 0 from the universe. So each element is contained in exactly half the sets. So that implies a feasible solution can take that for all u, xu is 2 over m. Okay. Good. And what's the cost of this solution? It's 2. Implies the opt of LP is at most 2. Just make sure we're all on the same page, right? The cost in the LP was just the sum of the XUs. And the constraints were that for every element, the sum of the XUs for all S, I should say, for all sets S, XS is 2 over M. So the constraints are that for any element E, the sum of all the XS's for S containing E should be at least 1. Right. So this is just equal to 1 over the number of sets containing E for some E. Okay, so good. Meanwhile, for the integer solution, okay, well, it's going to follow from linear algebra, right? Suppose we have a solution with q minus 1 sets S alpha 1 up to S alpha q minus 1. And what you're telling me that the union of S alpha I, or the intersection of the complement of S alpha I, where I goes from 1 to q minus 1, you're telling me this intersection is empty. There's nothing that's not covered by any of them. Okay. But what does this mean? What is this intersection? This is equal to the set of all E's, or not that it's empty, but that I guess it's the set 0.
0 is
Yeah, it's not in the universe. Yeah. So what is this set? It's the set of all E's such that for all I from 1 up to q minus 1, alpha I dot q dot E is equal to 0. Right? So we started off with a q-dimensional space, a q-dimensional vector space. And here, this is the set of all elements satisfying q minus 1 constraints, q minus 1 linear constraints. So its dimension is at least 1. Okay. So in particular, it's non-empty. this is an at most q minus 1 dimensional space. Sorry. Sorry, that's not what I meant. Q minus 1 linear constraints implies it's at least one dimensional, which implies it's non-empty. Okay? So that's a contradiction. So you need at least Q sets. Okay. Questions? Okay. So now I want to touch on the last thing, polynomial time approximation schemes. So here the idea is, well, let me just start defining some of these terms. So let me look at minimization problems. You can define similar things for maximization problems. Okay. We say a problem admits a p-TAS. This is a polynomial time approximation scheme. Actually, just before I let me say one more thing before I finish with integrality gaps. There are actually stronger things you can do. So with integrality gaps, you're just saying that this particular LP relaxation can't give me something better. A stronger statement that you could hope to make is, unless p equals np, there's no polynomial time algorithm to do better than a log n approximation. Okay, right? So, forget about even using LP relaxations at all. No matter what you do, unless p equals np, there's no better approximation ratio achievable. So actually, for the set cover problem, it's known, this is a theorem due to Fega in 98, that you can't really do better than natural log of n unless you can solve sat in time n to the log n or something like that. Okay. The best known algorithms we have for sat run an exponential time in n. N to the log n is way cheaper than that. So that gives strong evidence that we don't expect to beat natural log of n. So the proof of that doesn't use it uses some machinery that we're not going to cover at all in this class. Namely, it builds upon something called the PCP theorem. PCP stands for probabilistically checkable proofs. I guess if you want to hear about that, take a complexity course or go read about it. Okay. So, anyway, I just thought I would mention it. You should be exposed to its existence. Okay, so back to p-TASes, f-p-TASes, and f-prasses. So we have some minimization problems, set cover, or whatever else, vertex cover, etc. And we say it admits a p-TAS if for all epsilon in 0, 1, and also for all problem sizes n, can achieve we can achieve for all epsilon fixed, we can achieve 1 plus epsilon approximation in time poly n. We write it as n to the f of 1 over epsilon. Okay, so think of epsilon as a fixed constant, 0.1 or something. So what I'm saying is, for any fixed constant epsilon you give me, then it's possible, there is an algorithm that gets a 1 plus epsilon approximation in this time. F of 1 over epsilon could be terrible. Okay, it doesn't have to be polynomial in 1 over epsilon. It could be 2 to the 2 to the 2 to the 1 over epsilon or something. But if it's a fixed constant, then this is a polynomial. Okay? So meanwhile, in FP-TAS, F stands for here fully. So a fully polynomial time approximation scheme is one where for all epsilon, we can get time polynomial in n over epsilon. So you're not allowed to have crazy dependencies on epsilon. In particular, epsilon, you shouldn't have epsilons in the exponent of n. And an F-pras is a fully polytime randomized. Well, there's no, I guess it should be F-patras, but you can't really pronounce that. Approximation scheme. And here we allow ourselves to use randomized algorithms. And these randomized algorithms are allowed to have some probability of failure. So the time is poly n over epsilon, but allowed to give a wrong answer, meaning not wrong answer, but say not achieve 1 plus epsilon opt with probability at least, probably at most a third or something. Good question. Why a third? So suppose I could achieve this third guarantee. And I really wanted to achieve a guarantee of, say, delta as opposed to a third. So what would I do? Make a bunch of different runs, right? And take like the median run or something. Okay, so basically the way you define it, when you define this F-pras, the way you specify that constant doesn't really matter. Yeah. I guess, why is that the case? Well, maybe not in this situation. So a third is a good thing for kind of bounded error polynomial time algorithms. Maybe, what's one nice thing about a third? So suppose, forget about F-prases. The reason I picked a third, I'm now digressing slightly, but the point is, if you have an algorithm that outputs a number and you have no way of verifying that that number was correct or not, okay, well, if you know that the number is failing you with probability at most a third, then if you take many trials and take the median number that showed up, it'll be good with probability, with high probability. Okay, that's not true with a half, right? So a third is sort of the number of the form 1 over integer, where integer is as small as possible, which works. Okay, so yeah. Okay, so good. So I want to show examples of p-TASes and fp-TASes and f-prases. So I'll show a p-TAS, and I'll also show an fp-TAS for knapsack. And I'll show an FPRAS for counting number of solutions to a DNF. I forgot the year. This is so this is due to Karp, Luby, and Madras, I believe, and I don't remember the year right now. Knapsack, well, there's been a sequence of papers. I'm not going to cover the most efficient FP TASs or P TASs, but from searching around, it seemed that the most efficient FP TAS for knapsack was due to Eugene Lawler in '79, but maybe I missed some reference. These are examples. I should have said these are examples. Okay, so let me define knapsack. So we're given. So we have a knapsack. With capacity W, and we're also given items with weights W1 up to Wn and values V1 up to Vn. Yeah.
You just remind what knapsack is?
I'm defining the problem.
Oh, okay.
This is the definition of the problem, sorry. Yeah, so problem statement. Is this, okay, so we have a knapsack with capacity W. I literally mean a knapsack, like we have a backpack, okay? And it can hold W pounds worth of stuff. And we have items with the following weights. So item I has weight Wi and value Vi. And we want to pack our knapsack to maximize the total value. So this is our goal. Okay. So we could write this as maximize sum I from 1 to n of the value of item I times xi, which tells us whether we took it or not, subject to the constraint that the sum I from 1 to n of wi xi is at most w, and that for all I, wi is either xi is either 0 or 1. Okay, so this is knapsack. So suppose we relaxed the integral constraints, this integral constraint to suppose we relax this. I like this one. This color is more visible, I think. So suppose we relax this to xi is between 1 and 0. Okay. I don't want to relax it to just say xi is bigger than or equal to 0, because if there's a really valuable item, you might be incentivized to take it multiple times. Okay, which there is a variant of knapsack where that's allowed. I think it's called multi-knapsack or something. But for me, you can't purchase multiple copies of the same item. Okay, you can just take a subset of the n items you're given. So suppose you had this fractional version of knapsack. What would the optimal solution be? What'd you do? Yeah, so for fractional knapsack, sort items in decreasing order by vi over weight of I. So which has the best, which gives you the most bang for your buck, most value per pound. And take fill up knapsack in this order, right? So put as much of item 1 in this sorted order as you can, and if you still have space, put item 2 until you run out of space. And on the last item, you might only be able to take a fraction of it, but you'll take whatever fraction you can fit. Okay? So what's a natural greedy algorithm that you might hope? So by the way, knapsack is NP hard. Okay? But I claim that there are dynamic programming solutions to knapsack, right? So exact integral knapsack one thing you could do is you could get time O of n w. Okay, so here what you do is you say f of I w is equal to the most value achievable. Let me make myself some. Let me not cram myself. So how do you get this? You say f of I w is the max value achievable, or let me write it as b. F of IB is the max value achievable if we have b space left and only take items from the set 1 up to I. Okay? So at the end of the day, what we want is f of n comma w. How do you get f of I comma b? Well, you can either take the ith item or not take it. So you can either f of ib is equal to the max of f of I minus 1b, where you don't take the item, or f of I minus 1, or, so let me write it like this, f of ib is equal to 0 if I is equal to 0. Otherwise, it's equal to the max of f of I minus 1b and vi plus f of I minus 1b minus wi if b minus wi is not negative. So you can write a recursion like this, okay, and fill up this table using dynamic programming. So great, we have a fast algorithm for knapsack, but knapsack is NP hard. How is that possible? Yeah, W is, right, when we say polynomial time, we mean polynomial time in the bit representation of the input, right? And W, to write down W as part of the input takes log W bits. So to actually be polynomial time, we would have to spend, polynomial time means polynomial in n and log W. So n times W is not acceptable. And you could also define V to be the sum over I of Vi. And you can also get time O of NV. That's another thing you could do for knapsack. How is that? You define f of I comma p as being, it's another dynamic program. Have people seen this, right? How would you get, so NW for knapsack is according to this. You could also get NV. How would you define f of I comma p? Yeah.
The minimum weight
minimum weight to get value exactly v using only items from the set 1 up to I. Okay, and I'm not going to do it. You can set up a recurrence to fill this table out as well.
Is this like the dual of that?
I think they're just different algorithms. Yeah. Yeah, I think they're just different algorithms. Okay, so great. So now what we want is a good approximation algorithm. So so we know how to do exact integral knapsack, and we know how to, but it's slow, right? We don't like W, we want log W. And we know how to do exact fractional knapsack. So what's a natural greedy algorithm that the exact fractional knapsack suggests to us?
Just fill it up until you can't anymore.
Yeah, so approximation algorithm attempt for integral knapsack. Sort by vi over wi. Keep taking items till there's no space. Okay. So I claim, though, that we're going to have to tweak this algorithm, but I claim that just as written, we can do very badly. Anyone have an example of an input where we would do badly? Yeah.
But if you just have one that covers one that covers n of them, and the one that just covers one has a cost 10 bits lower, then you can just put the first one and you cannot put the second one, whereas you could just put the second one as very large first.
Right. So you're saying there might be an item that has a better ratio, which has a very small weight and very small value, but just a better ratio. But then there's a big item that has a lot of weight that once you put the first item, you can't fit it. Right? So that's right. So for example, bad case, you could imagine, for example, v1 equals 2 and w1 equals 1, whereas v2 equals w and w2 equals w. Right? So greedy would take this item first because it has the better ratio, but then you can't fit this one. Whereas opt would have just taken v2 and gotten w value. So this implies that you get an unbounded, or really, not better than, and I could have made this 1 plus epsilon. Not better than a W approximation. So that's not great. Here's a modified greedy algorithm that I claim does pretty well. Take either 1, the output of greedy, or 2, the most valuable item. I'm imagining that I've already filtered out items that have weight bigger than W. I mean, if an item has weight bigger than W, there's no reason to acknowledge its existence. Okay, so claim is that this algorithm is a 2 approximation. Okay. And we're going to prove a lemma, and then we're going to see how to exploit that lemma to get a p-TAS. Okay, so let me write a lemma here, lemma 1. Suppose greedy takes items v1 over w1 greater than equal to v2 over w2 greater than equal to vk minus 1 over wk minus 1, then no room for kth item. Then the sum I from 1 to k of vi is at least opt. Okay, that's the lemma. So proof, the proof that modified greedy is a 2 approximation, well, I claim it follows immediately from the lemma. Why is that? Are people okay with the statement of the lemma? Yeah.
I was adding VK and most double, otherwise it would be bigger.
Wait, sorry, say it again.
If you add VK, you could almost double, because otherwise you would just fall into it. Does that make sense?
So wait, by the way, this sum includes vk.
Yeah, so if I take V1 to VK minus 1,
Yeah.
then by adding VK,
Yeah.
I can almost double the value.
Yeah.
Because
Right.
if I did more than doubling the value, then I would be in the second case where I could just get it alone.
Right. I mean, right. Or another way of saying the same thing that you just said is this sum of vi from I is 1 to k is just v1 plus dot dot plus vk minus 1 plus vk. So one of these is at least opt over 2 by the lemma. Okay. Okay, so that's the proof. So now we just need to prove this thing. So how would you prove this lemma? And I claim you should think about this thing. Yeah.
So we know that the fractional abstract has value in the value of the fractional abstract is the sum of the first k minus 1 item plus a fraction of the last one.
Yeah, exactly, right? So we know what opt is for this thing, right? Opt for this thing would take the first k minus 1 of these items, and then it would take some fraction that's less than 1 of the last item. Okay? So we know that that's the opt. That's what opt would get, the optimal profit for the fractional solution. And we know that the integral opt can be at most the fractional opt. And this number is at most, this number is bigger than the fractional opt, right? Because we're not just taking a fraction of the kth element, we're taking the whole thing. So proof is that the sum I equals 1 to k of vi is even bigger than fractional knapsacks opt. Okay, so that's it. Okay, so now I want to give a p-TAS. Okay. And I think the main observation that I want to use for this p-TAS is that if no item has value bigger than epsilon times opt, then greedy achieves at least 1 minus epsilon opt. Yeah, so I should say I defined p-TAS, f-p-TAS, etc. for minimization problems, but you could also define them for maximization problems. So with the minimization problems, you want to get at most 1 plus epsilon opt. For maximization, you want to get at least 1 minus epsilon opt. Okay. So why is this true? Right. This is true because of the lemma. Right. So greedy gets the first k minus 1 things in this sum and misses out on the kth. But if no item has value more than epsilon times opt, then missing out on the kth is at most losing us epsilon times opt. So the sum of the first k minus 1 is at least 1 minus epsilon opt. Okay. So also, this is observation 1. Observation 2 is at most 1 over epsilon items can have value at least epsilon opt, or bigger than epsilon times opt. Oh, now, well, what do I mean by that? At most, 1 over epsilon items in the optimal solution have value bigger than epsilon opt. Right? Otherwise, opt would be better than opt. Okay, so now, what's a p-TAS? Remember, epsilon is a constant. Okay, so give me some algorithm that, given a fixed epsilon, runs in polynomial time. Your exponent is allowed to behave as you want in terms of epsilon.
I take a set of size 1 over epsilon.
Yeah.
And I'm trying to bring it, complement it to. I'm running greedy algorithm first.
Yeah, exactly. So the algorithm, so just to repeat what Jarek said, this is just an algorithm. Guess a set S of size at most 1 over epsilon. Guess a set S of size at most 1 over epsilon, which would be the set of elements in optimal solution of value bigger than epsilon times opt. That's step 1. 2, and you're going to put S in your output. Okay. Well, first we're going to check to make sure it actually fits in your knapsack. If not, just keep going on in the loop, continue in the loop. Okay, if it does fit in your knapsack, you guessed S. Then 2, remove all items remaining which have value bigger than anyone in S. Right? So S is supposed to be the set of items with value at least epsilon opt. Okay, so now that we've guessed S, we can remove all the items which have value bigger than them because we're assuming that that is the set of big items. And then 3, run greedy on what's left. What's the running time of this algorithm? Yeah. So n to the 1 over epsilon plus 1. Or, yeah, I guess there are some m's here, depending on how many sets you have. So let me just say O of n to the 1 over epsilon times, poly of nm or something. I'll be less specific. Yeah. Okay. And the claim is that our profit is at least 1 minus epsilon times opt. What's the proof of that? So suppose in some iteration we're actually going to guess S correctly. Suppose we guess S correctly. We know that opt of S, we know that opt is equal to the value of S, so the sum of the values of items in S, plus opt prime, which is the best packing of the small items, the items with value at most, with value at most any item in S. Meanwhile, what do we achieve? We achieve V of S plus greedy plus what greedy achieves. So we need to show that this thing here is at least opt prime minus epsilon of opt, let's say. Okay. So greedy what do we achieve with greedy? We know that this item vk, so k is the last is the item that we don't take, the first item we don't take, right? What do we know about vk? I mean, we know something from here. We know that, right? We know that we filtered out all the items with high value. So we know that vk is at most epsilon times opt, because S is the set of items containing S is the set of items with epsilon opt value for each item. And we also know that the greedy output plus vk is at least opt prime. That's lemma 1. Which implies that greedy achieves opt prime, achieves at least opt prime minus epsilon times opt. So that's it. Okay, so that's it. Questions about that? Okay, so if there are no questions, I guess next time I'll show you an FP task for knapsack and an FPRAS for another problem. Next week, I will not be here, but we'll have 2 guest lectures, one on Tuesday, one on Thursday. Because I won't actually be in Cambridge, I won't be here for office hours, but I'm very happy to, if people want to attend my office hours, I'm very happy to do Google Hangout or something. Okay, so you should send me an email if you want to chat. Okay, good. And yeah, as I said, PSET 4 will be out tonight. Okay.